Hey everyone, welcome back to Chem Story. Today we're going to look at one of the most important reactions alcohols can go through, oxidation. We'll explore what kinds of products you get, what reagents are involved, and how the mechanism plays out, step by step. By the end of this lesson, you'll have a clear picture of how alcohol oxidation works, and you'll know how to predict the outcome based on the structure of the alcohol. Alright, let's jump in. Let's start with what's called the oxidation ladder. It's a helpful way to see how different organic molecules are connected through oxidation and reduction. On the far left, we've got the most reduced form, the alkane. As you move to the right, each step represents a higher oxidation level. Alkanes can be oxidized to alcohols. If it's a primary alcohol, it can go further, first to an aldehyde, then all the way to a carboxylic acid. Each step adds more bonds to oxygen or removes hydrogens. And if you go in the other direction, from right to left, that's reduction. You're gaining hydrogens or losing oxygens. Let's start with primary alcohols. In these, the OH group is on a carbon that's connected to just one other carbon. When you oxidize a primary alcohol, you can get either an aldehyde or a carboxylic acid. If the conditions are mild and controlled, it stops at the aldehyde. But if the conditions are harsher, or there's water in the system, it keeps going, all the way to the acid. So in the end, what you get really depends on the reagent and the reaction conditions. Now let's take a look at secondary alcohols. Unlike primary alcohols, which can go to aldehydes or even acids, secondary alcohols only get oxidized to ketones, and that's where it stops. Now, what about tertiary alcohols? They don't get oxidized under normal conditions. Why not? Because for oxidation to happen, there needs to be a hydrogen on the carbon holding the OH, and tertiary alcohols don't have one. So without that hydrogen, you can't form a carbonyl, and the oxidation just doesn't happen. Let's take a look at how a primary alcohol gets fully oxidized, first to an aldehyde, and then to a carboxylic acid. We'll go through the key reagents, the conditions needed, and the mechanism behind this two-step process. One of the most common ways to oxidize primary alcohols to carboxylic acids is by using chromic acid. It's a chromium-6 oxidant, and we usually make it in situ by mixing chromium trioxide with water and sulfuric acid. Other chromium-based reagents, like dichromic acid or sodium dichromate, work in the same way. They all generate the same active Cr6+ species. So when we talk about chromic acid oxidation, we're really referring to this whole group of chromium oxidants that behave similarly. Jones reagent is a mix of chromium trioxide, sulfuric acid, and acetone. It's a strong oxidant that turns primary alcohols into carboxylic acids. You can also use potassium dichromate instead. It works the same way. And here's a nice feature. As the reaction goes, the color changes from orange to green. That's Cr6+ getting reduced to Cr3+. Here's a visual that shows exactly what happens with the Jones reagent. Before the reaction, the solution is bright orange. That's the Cr6+. But once the alcohol gets oxidized, the color shifts to a deep green. That green comes from Cr3 plus the reduced form of chromium. And this kind of color change is really useful in the lab. It gives you a quick, visual sign that the oxidation actually happened. Now let's take a quick look at how this oxidation works. It happens in two steps. First, the alcohol becomes an aldehyde, and then that gets oxidized again to a carboxylic acid. At the same time, the chromium reagent gets reduced step by step. So while the organic molecule is being oxidized, the metal is being reduced. That's the redox process in action. Let's start with the first part, turning the alcohol into an aldehyde. The lone pair on the alcohol oxygen attacks the chromium center in chromic acid, and that forms a chromate ester. Next, a water molecule steps in as the base. It pulls off the hydrogen from the carbon next to the oxygen. That sets off an E2-like elimination. Electrons shift in, the bond to chromium breaks. Then, after deprotonation, the aldehyde is formed. So that's the first half, from alcohol to aldehyde. Now let's move on to the second step, turning the aldehyde into a carboxylic acid. This part also uses a chromium oxidant. First, the carbonyl oxygen gets protonated, which makes the carbon more electrophilic. Then water adds in, forming a hydrate with two OH groups on the same carbon. Under acidic conditions, this hydrate reacts with the chromium species and forms another chromate ester, just like before. And again, an E2 type elimination kicks in. Electrons push in, the bond to chromium breaks, and in the end, you get a carboxylic acid. Now let's talk about how to stop the oxidation at the aldehyde without going all the way to the acid. To do that, you need two things: a selective oxidizing reagent and a dry, water-free environment. If there's water around, the aldehyde can turn into a hydrate, which makes it much easier to keep going to the acid. So the key is using a mild reagent and keeping the system anhydrous. One of the best reagents for stopping at the aldehyde stage is PCC, pyridinium chlorochromate. It's mild, selective, and a go-to choice for turning primary alcohols into aldehydes. Like chromic acid, it uses chromium in the +6 oxidation state, but the key difference is that PCC works under dry conditions, usually in a solvent like dichloromethane. And that's important, because without water, the aldehyde won't keep going to the acid. Another option is PDC, pyridinium dichromate. It works a lot like PCC, but it's neutral instead of acidic. What really matters with PDC is the solvent. In dichloromethane, it usually stops at the aldehyde, but if you use DMF, especially with excess PDC, it can push further and give you a carboxylic acid. So with PDC, the outcome depends not just on the reagent, but also on the solvent you choose. Now here's another great method, the Swern oxidation. This one doesn't use chromium at all. Instead, it uses DMSO, dimethyl sulfoxide, as a sulfur-based oxidant. But not just plain DMSO, it has to be activated first, usually by reacting with oxalochloride, or sometimes TFAA. Once activated, it becomes a very effective oxidant, especially for turning primary alcohols into aldehydes. And the best part? It runs under mild, almost neutral conditions. No heavy metals, no strong acids, and no risk of over-oxidizing to the acid. So if you're working with something sensitive, or you just want a greener alternative to chromium, Swern oxidation is a great option. Let's take a closer look at how the Swern oxidation works, step by step. First, DMSO reacts with oxalochloride and forms a highly reactive intermediate called a sulfonium salt. During this step, gases like carbon dioxide and CO are released, and that helps push the reaction forward. Then the alcohol comes in and attacks the sulfonium species, forming another intermediate. At this point, triethylamine acts as a base. It pulls off a proton, which sets off a chain of elimination steps, and that gives you the aldehyde. So even though the mechanism might look a little complex, it's really just a smart sequence of activation, substitution, and elimination. And the best part is, it all happens under mild, non-acidic conditions. Here's another great method for turning primary alcohols into aldehydes, the Desmartin oxidation. It uses a reagent called Desmartin periodinane, or DMP for short. DMP is a hypervalent iodine compound, meaning the iodine forms more bonds than usual, and that's what makes it such an effective and selective oxidant. It's mild, easy to handle, and a lot less toxic than chromium-based reagents. So if you're looking for a cleaner, more environmentally friendly option, DMP is a solid choice. Now let's break down how the Desmartin oxidation works. It starts with the alcohol attacking the iodine center on the DMP reagent. That forms a bond between the two, and at the same time, one equivalent of acetic acid is released. Then a base, usually acetate, pulls off the hydrogen from the carbon next to the oxygen. That sets up an E2-like elimination. The electrons push in, the leaving group pops off, and we're left with a carbonyl, either an aldehyde or a ketone. Let's finish up with secondary alcohols. These get oxidized to ketones, and that's it. No further oxidation under normal conditions. All the reagents we've talked about, chromic acid, PCC, PDC, Swern, and Desmartin, work great here. So the choice really comes down to what you're looking for: mild conditions, low toxicity, or compatibility with other functional groups. It's a simple, reliable transformation. Secondary alcohols give ketones. Now let's see how secondary alcohols oxidize with metal-based reagents. Chromium systems, like sodium dichromate in sulfuric acid and water, or chromium trioxide in a similar acidic mix, work quickly and cleanly, giving you a ketone every time. So they're powerful and reliable, but keep in mind the toxicity and waste disposal issues that come with chromium. Now let's talk about some milder options, like PCC or PDC. They oxidize secondary alcohols to ketones under gentler conditions, which is super helpful when you're dealing with sensitive or complex molecules. Even bulky structures react smoothly, like the example here with PCC and DMF. So with these reagents, you get both selectivity and control. Finally, let's wrap up with non-metal oxidants, like Swern and Desmartin. These are great when you want a clean oxidation without dealing with metal waste. Swern uses DMSO and oxalyl chloride, while Desmartin uses an iodine-based reagent. Both give clean ketones under mild conditions, and they're gentle enough for functionalized molecules too. So whether you go with something strong or mild, metal-based or not, you've got a full set of tools for oxidizing alcohols. And that flexibility is exactly why this reaction is so powerful in synthesis. Thanks for watching Chem Story, and as always, I'll see you in the next video.